Okay, in the next couple of lessons, we're going to be dealing a lot with circuits, and this is not something that's easy to grasp. And then ordinarily, when we're in class, we would be doing a lot of experimentation to kind of figure out these concepts. But without that ability, I'm going to try to give you a visual aid that I think everybody can sort of at least relate to. Okay, imagine you have a tube of toothpaste. Okay, and you have a very small opening at the top, and you start squeezing that toothpaste with your fist. You start squeezing that tube as hard as you can. Okay. Now, if you've ever done this, and I'm sure that you probably have, okay, the rate that that toothpaste comes out is all dependent upon the opening at the top. Okay. Now, if that opening is clogged up and really restricted, so there's barely any room there, then you don't get much flow of toothpaste. No matter how hard you squeeze, it comes out a little faster, a little slower, but that toothpaste, that hole really sort of restricts it. If that is wide open and it's a really big hole there, you can empty this toothpaste tube out really easily just with a small amount of force squeezing. Now, electrical circuits are not exactly like that, but this is a decent analogy to be able to deal with three terms we're going to use a lot, three measurements, okay? Voltage, current, and resistance, okay? Now, voltage is the amount of potential energy that is essentially emptying a battery, so to speak, of these charged particles. Now, it doesn't operate exactly that way chemically, but it's a decent way to think about it. In this case, the voltage is the oomph, it's the squeeze, it's the push. The amount of squeezing that you do, and we'll come back to this analogy as we hit different circuits to analyze, the force that we're squeezing with represents the voltage on, say, a battery. Okay, whether it's a 9-volt battery or a 12-volt battery, it has a certain amount of oomph to it, a certain amount of push. Okay, and that's what we would represent here with the squeezing. The flow of the toothpaste that comes out, we would call that the current. Okay. So the current that comes out of a battery or that flows through a particular circuit, we would kind of think of as the rate that the toothpaste is coming out, like how much is coming out, how quickly is it flowing. Okay. And then the resistance, which we haven't dealt with much up till now, the resistance would be that size of opening. Every circuit has things that the electricity is powering or particular materials that the electricity is flowing through. And that's kind of like this opening right here. That opening can get clogged up and get really narrow and restricted, or that opening can open wide and all of a sudden things empty out real quick. So the amount that is restricted and not allowing that toothpaste to flow out is kind of like what we would call electrical resistance. It's sort of things that get in the way. It's these obstacles that get in the way of the electricity that does not allow the current to flow freely. Okay? And we're going to come back to this in a lot of different settings to try to take that and map it out to a particular electrical circuit. Now, let's take that and let's look at how you're going to see things drawn. Okay? We're going to draw circuits as though we're going to try and keep them fairly rectangular in nature just so that we can see them easier and analyze them. But this little symbol right here represents a battery, and you'll usually, if you have a particular voltage on that battery or amount of potential energy that it can produce, we would have that written right there. So in this case, it's 9 volts. This represents a wire, and we're assuming a wire that allows electricity to flow through it essentially freely. Okay? It allows these charged particles to go through it. That wire comes around, and then we see it go through this little squiggly line. We're going to use that to represent a resistor. Okay, now a resistor in our case with the toothpaste was something that restricts that and doesn't allow it to move as freely as it normally would. Okay, so we have resistance, we have voltage, and then sometimes you'll see a capital A here that represents the current. Now the first thing we're going to get used to is dealing with something called Ohm's law. Okay, Ohm's law is what we're going to analyze a lot of these circuits with. Okay, and Ohm's law is voltage is equal to the current times the resistance. Okay, now that's the way you could write Ohm's law, but you can rearrange this to get any one of those variables by itself. So let me give you an example here. Okay, in this case, we see that our voltage is 9 volts. We see that our resistance is 36 ohms. Okay, now that's a weird looking symbol, but that symbol is for resistance. It's called ohms, named after that right there. Okay, and all we have to do now is take a look and go, all right, what are we really looking for here? We have the voltage, we have the resistance, we don't know the current. So if I were to rearrange this and get I by itself, the formula would say I equals V over R. So I'm going to take the voltage, which is 9 volts, divided by the resistance, which is 36 ohms. And when I do that, I'm going to get a unit of amps. And if we went back to our previous video that had all these different breakdowns of what those units mean, we could go through and see the cancellation. But in this case, I'm just going to show you what it ends up with. 9 divided by 36 gives us less than 1. This is 0.25 amps. That tells us how fast current would be moving through. What's the flow of current through this entire circuit? Okay, so I would write this as 0.25 amps. We write it right next to one of those wires, and basically that resistor slows the entire thing down. It can't move faster through one side than it does through another, just like if we squeeze the hole on a toothpaste. If we restrict that hole to make it even smaller, the entire flow of toothpaste changes. It's not like it comes out fast in one spot and slow somewhere else. It's all slows down basically to the same pace. Okay? Now let's take a look at this circuit over here. Notice I drew the resistor over on the side. It doesn't really matter. It's still a wire going through something that's slowing down this electricity, that's impeding the progress. It doesn't really matter where we draw it. But here we have current. And we've got a 9-volt battery. So when I look up here, I have my voltage and I have my current, but I don't know what this resistance right here is. Okay, so I can calculate that. Resistance would be voltage divided by current this time, so it's a lot like this formula, but it's just rearranged to get R by itself. I've got 9 volts divided by 4.5 amps, and I take 9 divided by 4.5, and I'm going to get a value of 2 ohms. So in order to get 4.5 amps of current, I have to have a lot less resistance. This is equal to 2 ohms. Okay. Now, in our third one over here, notice we have the current labeled. We've got the resistance in the circuit label, but we don't know the voltage on the battery. So if we just rearrange this now back to the original formula over here, volume equals current times resistance. I'm sorry, not volume. Voltage equals current times resistance. Voltage is going to be 0.33 amps times a resistance of 18 ohms. And that's going to give me a value of 6, which would be a 6-volt battery. Okay. And we're going to get accustomed to doing these simple things like this before we start putting in combinations of lots of resistors and multiple pathways and some different things that happen in typical circuits you'll see in everyday life. Okay, so we're going to start with some simple things in your homework. Be looking at these and make sure you can get down your units. Really, the purpose of this first homework assignment is to get used to the units for each one of these measurements, whether we're dealing with voltage, resistance, current, power, energy, whatever it might be. Just get used to what that means before we jump into a more difficult context.